Hobart School of Welding Technology presents Training in Oxyacetylene Welding, Cutting, and Brazing. Topic number 1, Lecture Discussion. Introduction to Oxyacetylene Applications. The objective of this topic is to be able to use the oxyacetylene process for welding, cutting, and brazing based on an understanding of its method of operation, equipment, and applications. Some forms of welding date back to periods before recorded history. Gold and brass had been welded as early as 2000 BC, and iron as early as 1000 BC. Yet welding as it is known today developed largely during the 19th century. The discovery of acetylene by Sir Humphrey Davy in the early 1800s did not result in its use for welding and cutting until almost 100 years later. In 1895, it was discovered that the combination of acetylene and oxygen produced a flame much hotter than any other known gas, about 6,000 degrees Fahrenheit. It was also observed that the combustion of equal amounts of oxygen and acetylene produced carbon monoxide and hydrogen, which burned in an outer envelope of flame along with oxygen from the surrounding air. This discovery, along with processes to produce oxygen in quantity, made acetylene welding a commercial possibility. The invention of torches, methods of placing oxygen and acetylene in tanks, and other developments over the following 10 years saw welding become an important tool for repair and some production. The World War I period of 1914 to 1918 accelerated the use of oxyacetylene for welding and cutting. Techniques which led to improved versatility and quality raised oxyacetylene welding to a scientific level, making it a manageable production procedure. Oxyacetylene is a gas mixture which can produce enough heat for welding, cutting, brazing, soldering, braze welding, hard surfacing, heating, and scarfing or gouging. The basic methods of operation for each of these applications are quite similar. Only a change in gas mixtures, torch tips, and in some cases filler metals is necessary. Oxyacetylene welding is used to fuse parts together by heating them with a flame obtained from the combustion of oxygen and acetylene. The flame produced by this combustion is one of the hottest at approximately 6,000 degrees Fahrenheit. The flame melts both the joint edges and the filler metal to produce a weld puddle, which is then controlled by the welder as he travels along the joint. Oxy-fuel cutting is a thermal process used to sever metals by heating them with a flame at elevated temperature, about 1,500 degrees Fahrenheit, and using pure oxygen to sever through the metal to produce the cut. This process is commonly used to cut from thin to extremely thick steel, but with special powders and equipment, it can be used to cut other alloys. Oxyacetylene brazing and soldering is also a thermal process. However, the base metal is not melted. It joins them by first heating to a suitable temperature, approximately 840 degrees Fahrenheit, and using a filler metal, which is melted and distributed between closely fitted surfaces to bond them together. The filler metal flows into the joint due to capillary attraction. Oxyacetylene braze welding closely resembles fusion welding, except again, the base metal is not melted. The filler metal used has a melting point well below that of the base metal. Oxyacetylene hard surfacing is an application where the surface of a material is built up with a special alloy which provides wear or impact-resistant qualities. The filler metal is deposited onto the surface with minimal penetration, much like braze welding. The oxyacetylene flame can also be used for flame hardening, forming or bending, straightening, wrinkle bending, and flame descaling. With an angled tip, the process can remove defective welds with the scarfing or gouging application. The equipment needed for this process consists of an oxygen and acetylene supply, pressure gauges and regulators, hoses with fittings and check valves, and a torch equipped with a suitable tip for the particular application. The oxygen supply is often in the form of a cylinder containing compressed oxygen. High volume users may pipe the oxygen from large tanks or tank trailers located outside the building. Oxygen is stored at very high pressures, up to 2,200 pounds per square inch, and because of this, cylinders must be treated carefully and inspected periodically. Oxygen is obtained from the air with a liquefaction process. By compressing and cooling to a very low temperature, the air becomes liquid. Air is mainly oxygen and nitrogen, which, as liquids, boil at different temperatures. The nitrogen boils off at a lower temperature, leaving the oxygen to be transferred to tanks for transporting. Acetylene is often supplied in cylinders at a much lower pressure for safety reasons. It may also be supplied from a generator, which uses calcium carbide and water to form the gas. Acetylene by itself cannot be safely used at pressures above 15 pounds per square inch. When it is stored in tanks at 250 psi, it is dissolved in acetone, which is a porous material made from pumice, balsa wood, or other material. The acetylene cylinder must also be treated carefully and inspected at intervals. Both oxygen and acetylene can be very hazardous if the cylinders are damaged or used improperly. Although the pressures used from the supplies are relatively low, the supplies themselves are quite high in pressure, and regulators must be used to reduce pressures to safe working levels. The pressure gauges and regulators are similar for both oxygen and acetylene and perform the same job. The gauges indicate the tank pressure and the working pressure, which is the pressure needed for a particular tip size. The regulators are made up of needle valves, springs, diaphragms, and gauges. Some reduce the pressure in one stage with one diaphragm and are the type recommended for manifold systems. Other regulators do a partial pressure gauges with two diaphragms. This is the type recommended for use with cylinder supply systems. The regulators for oxygen and acetylene are different and cannot be interchanged. To prevent interchanging, the oxygen connections have right-handed threads, and the acetylene and other fuel gases have left-handed threads. The hoses used with this process are specially designed to be used with oxy fuel systems and are color-coded to ensure proper use. The oxygen hose is green with right-handed thread fittings. The acetylene hose is red with left-hand fittings. For most applications, the hoses are 3/16 to 3/8 inch in size and 25 feet long. When the gas supply is within 25 feet of the work site, the 3/16 inch hose is adequate. The hose fittings or connections consist of three parts: a hose ferrule or clamp, which locks the hose onto the nipple, a nipple with a seating surface to match with the internal seat on the torch and regulator, and a swivel nut to tighten the connections. In assembly, each connection must be gas tight. The torches used with oxyacetylene can differ with each application. However, a change in tip and mixing chamber is all that is required. The torch is equipped with a handle, throttle valves, a mixer or injector chamber, and a series of tips with varying size orifices and shapes for different flames or applications. There are two general types of torches. The injector type uses acetylene at pressures less than 1 pound per square inch and depends on a suction effect from the higher pressure oxygen to draw the acetylene into the torch. The medium pressure type uses oxygen and acetylene of equal pressure in arrangements of 1 to 15 pounds per square inch. Some torches can be converted for flame cutting applications, or specialized cutting torches may be used. The tips used with this process are usually made of heavy-walled copper for greater resistance to reflected heat. There are many types and usages. Generally, the same type of tip is used for welding, brazing, soldering, braze welding, and hard surfacing, and is angled to allow comfortable use. Tips vary in size and length based on the volume of heat needed for the work. The orifice sizes generally range from 000 up to 12, numbers which represent measurements used by various manufacturers. Cutting tips also vary in size and shape, based on the volume of oxygen needed to cut. Other equipment necessary for the process includes a friction or spark lighter, sometimes called a striker, to light the torch, a set of tip cleaners to periodically drill out the orifices, filter goggles suitable for eye protection, gloves to protect your hands from open flame or sparks, and protective clothing. Wear long sleeves so that your wrists and forearms are covered. Wear high-topped shoes, if possible, and cuffless trousers, especially when cutting, to avoid catching hot particles and sparks. The flames used with this process include three types. The carburizing or reducing flame is the coolest of the three, at approximately 5,300 degrees Fahrenheit. Any flame that produces a feather beyond the tip of the inner cone is considered a carburizing flame. Because the flame produces some carbon, it is not recommended for fusion welding. However, it is used primarily for brazing operations. The carburizing flame can be adjusted to different degrees or settings. In the 2X flame, the carburizing feather is twice as long as the inner cone, measured from its tip. A 3X flame has a feather 3 times as long as the inner cone. The second type is the neutral flame, with a temperature of about 5,850 degrees Fahrenheit. It is neither oxidizing or carburizing, since there is no excess oxygen or acetylene to produce a feather flame. This type is used for fusion welding of steel and cast iron. The third type is the oxidizing flame, which has an excessive amount of oxygen in the mixture. Its temperature is approximately 6,300 degrees Fahrenheit. This flame is used for welding brass and bronze and for brazing galvanized steel and cast iron. It is easily identified by its short inner cone and a harsh hissing sound. The filler metals used with this process also differ with the application. For fusion welding, filler metal is supplied in compositions that match the material being welded. Sizes range from 1/16 to 7/16 inch in diameter and are usually 36 inches long. The American Welding Society classification for steel filler metals include, for example, RG45. The R stands for rod, the G stands for gas, and the 45 is used to indicate the tensile strength of the resulting weld in thousands of pounds per square inch. In this case, 45,000 pounds per square inch. The RG prefix is typical for gas welding filler rods. Only the tensile strength will change. For braze welding, the AWS classification consists of the prefix R and then a chemical symbol for each alloy in the rod. In this case, Cu for copper and Zn for zinc. Also included is a suffix which represents a particular grade and percent of alloys. The advantages of oxy-fuel welding are overwhelming. It can be used for many more applications than other processes. It is portable and not dependent on electrical power, as are the arc welding processes, and it is less expensive compared to other welding processes. However, it is a slow process to perform, requires much higher manual skill than most other processes, and the open flame creates a greater fire hazard. Instructions in this course are related to right-handed welders. For left-handed welders, positions and angles should be reversed. For example, in forehand welding, the right-handed welder holds the torch in his right hand at the right end of the joint and travels toward the left, adding filler metal with the left hand. The left-handed welder would hold the torch in the left hand, filler rod in the right, and would travel left to right. Instructions are confined to important details and are usually given only the first time. Whether specifically instructed or not, it is assumed that you will perform the obvious procedures, such as cleaning the workpiece, cleaning your torch orifice, lighting and properly adjusting the flame, positioning the inner cone the correct distance from the work, and other repeated operations. It is also suggested that you use the recommended pressures, angles, and other techniques presented throughout the course. As you gain experience, you will find that many other combinations will work as well, or perhaps better, for your own use. It is most important, though, that each weld be done to the best of your ability.